Hey everybody, welcome back. We're going to go into Module 3 here, and in Module 3, we're going to start looking at, in Module 2, we were looking at descriptive statistics, and that was great. I loved it. We were looking at how do we use data to display information really well, and I don't know if I showed you this website. I showed it in my in-person class, but at Gapminder, there's this beautiful website, Gapminder, and Gapminder has this great tool. If you go down to gapminder.org, they have tools, and they have this tool right here. And this is an incredible example of data visualization because this captures so many pieces of information in one really cool graphical display. And so here, I just want to show you this. And if you saw this before, maybe you could just 2x the video or play the scrub head forward, move the scrub head forward a little bit on the video. But here, what each of these balls represents is one country in the world. And the size of the ball represents the population. So here's India, here's China. And then the axes, over on the vertical axes, we have life expectancy or health. And down on the horizontal axes, we have gross domestic product per capita or wealth. So we have health and we have wealth. And these balls are the countries. So you can see here in India, the size of the ball represents the population of the country, and the color represents the region. So here are all of the Americas right here in green, including there's United States of America, but we also have Brazil down here and we have Mexico here. So those are all of the Americas, and here's all of Africa. And then here is Asia, and then over here is Europe. So the color of the balls represents the region of the world that the country is in. And you can see just by looking at this in 2022, right, that, South Sudan, you only earn $386 per year per person on average. But over here in Luxembourg, you're making $116,000 a year, or in Ireland, $114,000 a year per person for every person in that country. And you could run this scrub head, you could scrub this play head right here, and you could scroll back in time. And so this is really pretty extraordinary. You could see the history of humanity here. And you can see how both our life expectancy, our health, and then also our wealth has really increased over the last 150 years, particularly post-World War II. There you could see the balls all drop as people died during World War II. Big drops in life expectancy or health. That would be Germany, or that's Russia right there. Ukraine, right? But you could go through there and you could see which countries really dropped. Oh, there's Germany right there. That one's Germany. So that's the health and wealth of nations, but it's an illustration of data visualization and descriptive statistics, because this is so much easier to read than if you were just to go to gapminder.org and go look at the data. And so if you go to the data and you look at the data and you scroll down, here's the data. And so if we look for like GDP, so here's GDP per capita, and this is what the data looks like just for the wealth. Right? And it's really hard to make sense of that, just to see all of that data like that. So for the different years and the different countries, it's just a bunch of data. It's much easier to see that visualization we just looked at. So in the previous chapter, we were looking at descriptive statistics and how do we visually represent that. In this chapter, in this module, we're going to start looking at more ways that we could describe what's going on with our data. This time we're going to be doing it more mathematically. And so we're going to look at things like the mean, the median, the mode. So I made some notes here when I was going through the chapter. We're going to look at measures of location. So how is our data located? Mean, median, mode, percentile, quartiles. We're going to look at measures of variability or dispersion. How dispersed, or how much does our data vary? And we saw this when we were looking at this example right here previously. And I changed this to John's Acme Company and Robert's Parts Company. So if these were suppliers supplying us with things, these are the number of days it took for them to ship, for them to send something to us. It took 8 days for us to receive an order, 12 days, 8 days from the time we placed it. How long did it take till we received it? So John is like the measure of central tendency, the average or the mean is 10 on this data here. And it's also 10 on this data here. So on average, they take 10 days. Both of these companies take 10 days to deliver us a shipment once we place an order. But with Robert, there's much more dispersion. There's much more variability. It varies much more. The data, one time we placed an order, it took 30 days. Another time we placed an order, it took 2 days or 3 days. So there's much more variance or dispersion of the data here. It varies much more. And so that's something else you think about. So you not only think about what is that measure of central tendency, or what is the location of the data, the mean, the median, the mode, the percentile, the quartiles, we're going to learn about those, but also what is the variability or the dispersion of the data. And so variance, standard deviation, coefficient of variation, the range, the interquartile range. And then we're also going to see like how far is data and standard deviations away from the mean. And we're going to look at some theories, some theorems like Chebyshev's theorem, where it tells us if data is within a certain number of deviations, and we're going to learn what that means, of the mean, then we can say a certain percentage of the data is within a certain number of deviations of the mean. And the empirical rule is the same thing, but for a bell-shaped curve. So we're going to see that, and we're also going to see some notation. And so we're going to see different notation that statisticians use, that people who do statistics use to refer to different things. So for instance, we already understand what the mean or the average is. And when we're referring to a sample versus a population for the mean or average, we'll use different notation. And also for a population versus a sample, we use different notation. And remember, a population, like if we were to study students at Fresno City College, if we were to do that study of the entire population, we would have to study every single student, like 26,000 students. That's a lot. But if we just took a sample of the students, we might study 500 students or 200 students. And then based upon the results of our sample, we'll make inferences about the population. So that's referred to as inferential statistics. So when we're referring to a population in statistics, like how many people were in the population, we'll use the capital N. That's the number of people in the population that were being measured. And when we're referring to a sample, we use a lowercase n, the number of people that were sampled. And when we're referring to a mean or an average that was calculated on a sample, we'll use x with a bar over it. We call this x bar. And when we're referring to a mean that we calculated on a population, we'll use this notation right here, which is mu. It's called mu. And so if you wanted to see what that looks like, we could go over to ChatGPT and we could do a new chat and we could say, can you please show me the symbol mu or whatever it's called that's used in statistics to represent the mean for for a population. And so we'll see this symbol here. The symbol you're referring to is the Greek letter mu, and there it is right there. And it's commonly used in statistics to represent the mean of a population. Here's how it looks, right? So anytime you have questions about any of this stuff, you can come to ChatGPT and you could enter a little search and you can do it. I will be making notes like as I go through the chapters and continuing a list here of the different notations. But I really encourage you to do this too, so you have it handy, and you'll be able to reference that when you're like, what does that mean, the s squared or the sigma squared again? You'll be able to reference it as you're doing work and going through the course. So without further ado, let's jump in and start looking at chapter 3. And the first thing we're going to look at are descriptive statistics here, numerical measures. So numerical measures that help us describe what our data has, the data that we've gathered. So numerical measures to help us describe the data we've gathered. And we're going to look at measures of location and measures of variability. So again, here we have location and here we have variability. And with location, it's going to be mean, median, mode, percentile, and quartiles. Okay? And let's take a look at what these are here. So numerical measures, I think I'll just talk about it here. So I could take this picture. I'm going to take this picture. I'm going to go back over to ChatGPT. And so I have this picture downloaded right here. I'm going to grab this picture right here. And I'm going to say, can you please explain the measures of, and we'll just get that word here, the way I put it there. Measures of location, mean, median, mode. Measures of location, mean, median, mode. And then we also have percentile and quartiles. Percentile, and quartiles. Please also give me a simple example for each. Thank you. So we'll let this run for a second. While this runs, I will pause the video. So I like using ChatGPT here because I really want you to, one of the things I really want you to learn from this course is how to use ChatGPT to help you learn. And again, the paid version is much more effective than the free version. So, you know, if you can afford the $20 a month, you're going to get better results. That's just the way the technology works right now. But here it's explained for us those measures of location. So we've got the mean, and I really like the way that it explains it. And so here is the formula for calculating a mean for a population. And you can see mu here. That refers to a population. And again, in our notes. So again, we're learning new terminology, new syntax. We're learning how people who do statistics talk about things. But again, the mean for a population is referred to with mu. And so here we have mu. And what we're going to do is we're going to sum up each of the data points, x1, x2, x3. And so if we have this data set right here, 3, 5, 7, 9, that sum up x1, x2, x3, x4, that's what that xi represents, where I is each member of the data set. This would be the first member, the second member, the third member, the fourth member. This would be x1, x2, x3, x4. So we add those up and we divide by the total number. And notice here we're using a capital N. And so that capital N represents all the elements that are in a population. There's the capital N. And so we divide by 4. 24 divided by 4 is 6. So that's the mean. That's the average. Okay, and so the average tells us that on average, if this is like the number of yards that I could, you know, I don't know, throw a football, that's not very far, right? On average, I'm throwing the football 6 yards. Sometimes I throw it 9, sometimes I throw it 3, but on average, I throw it 6 yards. The median, so the median is the middle value when a data set is ordered from least to greatest. So when we have an even number here, right? So we have 3, 5, 7, and 9. The middle value is going to be these two values added, the two middle values added together and divided by 2. And so here you could see that being done. 5 plus 7 divided by 2 is 6. And then the middle value here, when you have an odd number for the median, is just going to be the middle value by itself. And that's going to be 5. So the median is the piece of data that's in the middle, the median. And you could remember that because in a road, we call the middle of the road the median, right? Like that's the median. And so that's the median when you're driving. And with data, the median, you know, when you're driving, the median's the middle of the road. And when you're doing statistics, the median is the middle of the data. If you have odd data, it's the single figure, which is in the middle. If you have even data, you add up the two figures in the middle and divide by 2, and that's your median. And then the mode is the number which occurs the most frequently. And so here we have two numbers that occur, so that's our mode, right? And so again, this is descriptive statistics, but we're describing the data, right, using other numbers. So we're getting an idea of like, okay, what do we know about our data? How can we talk about our data? What are the characteristics of our data? And instead of doing it visually, which I tend to like much better, right, we're starting to do it with different calculations. And so the mean tells us something, right? Like, you know, it's really important to know on average, you know, like some piece of information. On average, how much am I making each day, right? That's useful information. And then the median is the data. If we have a data set, it's the number which is right in the middle of the data set. And so, you know, that's the median right there and right there. And then the mode is the number which occurs the most frequently. And if we had multiple numbers in there, so like, can you please explain bimodal and multimodal to me, and also give me simple examples of each. right? So if we had, you know, the mode is the number which occurs, or the numbers which occur most frequently. And so this is our mode up here, the 7, right? Because that's the one that occurs the most. But what if we had numbers which occurred multiple times, like the 7s and the 14s? So this is known as bimodal, and both 7 and 14 is our bimodal answer. And multimodal is if we had more than 2, so 4 and 6 and 8. And so, you know, the numbers 4, 6, and 8 each appear twice and more frequently than the other values, making the distribution multimodal with modes 4, 6, and 8. And so you might be kind of like, okay, like what's the point? Well, these are just different ways to describe the data in our data set. We could talk about the mean. We could talk about the median, like what's the middle data point in our data set. You know, and we could also talk about the mode, which number occurs most frequently. And this is just another way to help us start to describe and talk about the data in a data set. And then we have percentile. So percentile shows us, like, you know, how much data is above and below a certain point. So a percentile indicates the relative standing of a value in a data set. For example, the 25th percentile is the value below which 25% of the data points fall. And so you could calculate any percentile with this formula here. And here's the notation we use to represent percentile. And again, you could see this on this sheet that I put together right here. LP is equal to P over 100 multiplied by N plus 1. LP is equal to P over 100 multiplied by N plus 1, where this is the percentile we want to figure out, the P. So where P is the desired percentile, N is the number of data points. So consider the data set 10, 20, 30, 40, 50, and the 40th percentile. So what is the number at which 40% of our data is below that point? So first we order the data, and then we calculate our 40th percentile. So 40 over 100 times N, there's 5 data points, 1, 2, 3, 4, 5. And we do plus 1, so 5 plus 1 is 6. We get 0.4 times 6, and we get 2.4. So at location 2.4, here's location 1, here's location 2, and location 2.4 is going to be 40% of the way between here, location 2, and here, location 3. So 40% of the way between 20 and 30, that's 10, 40% of 10 is 4, is going to be 24. So the 40th percentile corresponds to a value between the second and third values, 20 and 30. You can interpolate, so that's called interpolation, what I just did there when I was saying when it's 2.4, this is 1, this is 2, this is 3. So 2.4 is going to be 40% of the way between the second data point and the third data point. And I could interpolate what that means, and it means it's 24. So that's how you do the percentile. And then quartiles are just like percentiles, except in a quartile, we're looking at the 25th percentile, the 50th percentile, which is exactly the same as the median, and the 75th percentile. So let's first take a look at how the 50th percentile is the same as the median. You can see that here, or median. So here we have 4 data points on the left side of 12, and we have 4 data points on the right side of 12, which makes 12 the median. It's the thing in the middle, just like in the road, the median's the middle of the road. Here, this data point's the middle of our data set. It's 12, it's our median. That's also the 50th percentile. So, you know, if I wanted to, I could say down here to ChatGPT, can you please give me examples of calculating the quartiles using the percentile formula. And yeah, that's good enough. There we go. And so this will show us how we could have calculated these percentiles right here using the percentile, these quartiles right there using the percentile formula. But having these quartiles allows us to kind of see, right, at 7, 25% of our data is that way. At 12, 50% of our data is to the left. At 18, 75% of our data is to the left. And so here's an example of what that looks like down here when those calculate. So the first quartile is the 25th percentile, the 50th percentile, the 75th percentile. So here's a data set, made up a new data set. They're 11 point data points, so n is equal to 11. And so here the 25th percentile is going to be 25 over 100, 11 plus 1, that's 12. That's going to be 3. And so the third point will be here, 35, right? So that's Q1 is 35. And then Q2 is going to be 50 over 100, 11 plus 1, that's going to be 6. And so that's the sixth value in the ordered data set is 55. 1, 2, 3, 4, 5, 6. So there's 55. Thus Q2 median is equal to 55. And the 75th percentile is 75 over 100. And that's equal to 11 plus 1. So 0.75, we add that up, do this math, and then we get the ninth location. The ninth value is 70. We got 1, 2, 3, 4, 5, 6, 7, 8. Ninth location is 70. That's our 75th percentile. And so 75% of the data is 70 or less. And so that's how we use the percentile formula to calculate the quartiles. And here's how you do it with like odd numbers and interpolation. So you could pause the video here and you could take a look at that. So I'll just put that data up here, additional example with an odd number. What the heck, I'll just go through it with you. So 25 over 100, and we have 1, 2, 3, 4, 5. 5 plus 1 is 0.25 times 6, and that's 1.5. So here's the first one, here's the second one. So 1.5 is halfway between those two, which is going to be 15, and that's our first quartile. So 25% of the data is going to be 15 or less. Here's our 50th percentile. It's going to be at 3. That's going to be 1, 2, 3. 1, 2, 3. That's going to be 30. And the 75th percentile is going to be 4.5. So 1, 2, 3, 4, 5. 4.5 is going to be halfway between that. So interpolating between 40 and 50, 0.5, 50%, we get 45. And so that will be our 75th percentile. And we could ask ChatGPT, can you please tell me why are quartiles useful for describing data? And we'll see what ChatGPT comes up with this. I'm going to pause the video here while it prints out the answer. All right, it's finished printing out the results, and I read through them just to make sure that they would be useful to us. And you could go ahead and pause the video right here, and you could read through the first 4 pieces that they output, and I'll talk through them here in a second, but I just want to give you a chance to read through them. And then you could also pause the video right here, and you could read through the next portion. And I'll scroll down just another line so that you could see that last paragraph right there. And now we're going to look through these together, and I really like what it had to say. And there's one more thing that I want to add, so I'll add that, and I'll say, can you please provide me with a visual representation of quartiles in action, perhaps align with the numbers, showing the numbers in each quartile along the line. That'd be interesting. We'll see how it produces that, why I read this. So quartiles are useful for describing data because they provide a detailed view of the distribution of data, breaking it down into quarters, which is why it's called quartiles, that help us understand the spread, the central tendency, and the variability of the data set. Here are several reasons why quartiles are valuable. Measure of spread and variability. Quartiles divide the data into 4 equal parts, making it easy to identify the spread of data within each segment. So if we look down here at this example, imagine, oh, that's really nice here. So you can see here we have Q1, Q2, and Q3. And then here you can see that we have 1, 2, 3, 4 areas, right, with 3 separators, Q1, Q2, and Q3. We have 1, 2, 3, 4 areas, and these show like the different quartiles and the data in this example. So the first quartile here is at 35 because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 items. And with 11 items to find the first quartile, and let's see, I think we had 11 up here as one of our examples, right? So the first quartile here is going to be at 3, and then the next one will be at 6, and the next one will be at 9 with 11. So 3, 6, and 9. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where our different quartiles fall. And we use the percentile formula to find that. So our first quartiles, everything 35 or less. Our second quartile includes everything 50 and less. And our third quartile includes everything 70 and less. And so it starts to give us a visual representation of what our data looks like when we have this. So 15, 20, 35, right? And we could see that, and we could see this here, we could see that there. So that's a little bit of a visual on it, and that helps us see how the data is spread out and the variability. So quartiles divide the data into 4 equal parts, making it easy to identify the spread of data within each segment. By knowing where the first, second, and third quartiles lie, you can see how the data is spread out and whether it's concentrated in certain areas or evenly distributed. And so here you can see whether it's concentrated in certain areas or if it's evenly distributed. So this is like spread out more. And then here we go 50, 55, 60, 65, 70, 75, 80. It's more concentrated up here, and it's more spread out down to the left. So that's kind of interesting. And so again, what we're looking at here is how do we use different measures to describe our data. And so the median, the middle point right here is 55. There is no mode, right? There's no mode. There's nothing that occurs like more than once. So the mode would be the number which occurs the most. And then we could figure out the mean here if we wanted to. And that would be another measure of central tendency of like, what is the kind of central point? What is the average of this data? And so that's different measures we use. And then we also use the quartiles here to sort of see what is the distribution of the data. Quartiles are also resistant to outliers. So they're less sensitive to extreme values or outliers than other measures like the mean. So for example, the median Q2 is a measure of central tendency that is not influenced by outliers, making it a more accurate representation of the data's center in skewed distributions. So here, if we were to calculate the mean on this, so for this most recent example, can you please calculate the mean for this data? And we'll see if it actually picks up these data points here or goes somewhere else to get it. So we'll let that run for a second, but it'll be interesting to look at the mean here. So 10, 20, what do we have? 15, 20, 35, 40, 50, 55, 60, 65, 70, 75, 80 is approximately 51.36. So our mean is 51.36. The median is 50. But if we had taken this data set and we had added changed one figure, and what is the mean on this data set here? All right, and we'll put that there. And let me just get rid of this stuff there. And that's like that. And I will change this 80 here. I'm going to change that to like, 200, okay? And what is the mean on this data set here? And also, we'll do this. What is the mean and median on this data set here? So we'll let that calculate. And the mean is more susceptible to outliers, because when we put in a big figure right here, that's really going to change our average or our mean, whereas the median is still going to be like the median. The middle is another one. So up here, the median was 50 is 1, 2, 3, 4, 5, 6. The median is 55 right here. And again, the median is still 55 here. Previously, our mean was 51.36. Now, because we have 200, this data right there is an outlier. It really lies outside, the bounds, really away from the other data. And so our mean has now been stretched out it's been skewed out to 62.27. So that is a much higher mean. So I'm just checking to make sure I'm recording there. So that is interesting about how the mean works, and that's what this here says that quartiles are less sensitive to extreme values or outliers than other measures like the mean. For example, the median is a measure of central tendency that is not influenced by outliers, making it more accurate representation of the data center in skewed distributions. So it also gives us insight into data distribution. Quartiles provide insight into the shape of the distribution. For example, if the distance between Q1 and Q2 is shorter than the distance between Q2 and Q3, the data is skewed to the right. Conversely, if the distance between Q1 and Q2 is longer, the data is skewed to the left. And so here the distance between 31 and 50 is 15, but between 50 and 70 it's 20, right? So there's a greater distance here than here, and that gives us some information about what our data looks like and how is the data distributed. We also are able to use the quartile range to work with something called the interquartile range. And so that is the difference between the third and first quartiles. And so the difference between the third and first quartiles is 70. So 30 to 55 is 20, actually. I keep saying 50 because I think 50 is right there. So 35 to 50 is the difference between Q1 and Q2. And 55 to 70 is the difference between Q2 and Q3. So this one's 15, this one's 20. But to get back to this point right here, the interquartile range is the difference between the third and first quartiles. And so the difference between the third and first quartile is 70 versus minus 35, or it's 35. And so that range can be useful to help us identify outliers. And if we take that, 35 and multiply it by 1.5, so that any data points that lie more than 1.5 times the IQR above Q3 or below Q1 are considered outliers. So if the difference here is 35 between Q1 and Q3, and we multiply 35 by 1.5, so 1.5 times 35, that's 52.5. And 52.5, let me just bring this over here. If we have data that's like, 52.5, 35 minus 52.5, so 35 minus 52.5, right, is negative 17.5. So if we have data that's beyond negative 17.5 out here, or if we have data that is more than, and 1.5 times 35 is 52.5, if we have data that's more than 152.5 plus 70, or 122.5, so if we have data that's beyond 122.5, we call that an outlier. And we determine that outlier by using the interquartile range. And so interquartile range allows us to see how dispersed is our data. How much does our data vary? What's the variability? And so that's the IQR. So the location, these things help us sort of see what is the location of our data in a data set. What's the median? What's the most frequently, the middle? The median's the middle. What's the most frequently occurring one? That's the mode. What's the mean? What's this measure of central tendency or location? The average, the mean, the average. What are the percentiles? Q1, Q2, Q3, right? 25th, 50th, 75th percentile. And then those are the quartiles, right? What are the quartiles right there? And then we could calculate percentiles using this formula. So this shows us the location of data, allows us to start talking about how is the data located. And then over here, we could start to use these to talk about how dispersed is the data, how much does it vary. And so part of talking about the variance, or how much data varies in our data set, is the interquartile range. And so the interquartile range is 1.5 times Q1 minus Q3 minus Q1. So 70 minus 35 is 35, times 1.5 is 52.5. And if we subtract 52.5 from this, and we add 52.5 from that to that, anything outside that is considered something that's an outlier. So when I put in that data a point of 200 right here, that's definitely outside of 52.5 plus 70, or 122.5. 200 is way outside of 122.5. So 200 would be an outlier here. So these are all different terms and formulas we can use to think about our data and to understand how is our data located, the data set, how are the different pieces of data in the data set located, and then also how much does that data in the data set vary, how is it dispersed, and we're going to learn more about this here coming up in just a minute. I'm going to pause the video for a second and think about what to say next. I'll be right back. Okay, so now we'll take a look at this presentation here, and we're looking at measures of location and measures of variability. And so you can see, we'll just read through some of this, and I'll just talk about anything that sparks something that needs to be explained or discussed. If the measures are computed for data from a sample, they're called sample statistics. So again, we take a sample from a population so we can make inferences about the population, and that's known as inferential statistics. So if the measures are computed for data from a sample, they're called sample statistics. If the measures are computed for data from a population, they're called population parameters. And a sample statistic is referred to as the point estimator of the corresponding population parameter. So just some vocabulary that is used by statistics in statistics. And here we have measures of location. So we have the mean, we have the median, we have the mode. We also have a weighted mean and a geometric mean, and we've already looked at percentiles and quartiles. So a weighted mean would be like, it's good for, a weighted mean is good for like if I'm purchasing, let's say, I don't know, beans. I run a company that buys black beans, and I'm buying pounds of black beans, and sometimes I'm getting them at different prices. I might want to calculate my mean or my average based upon how much I paid for each pound. And so I could come back over to ChatGPT to get an example. Say, can you please give me an example of weighted mean using the example where I am buying black beans by the pound at different prices over time. So let's see what ChatGPT does with that. Let's walk through an example of calculating the weighted mean using the scenario where you're buying black beans by the pound at different prices over time. So purchase one, 2 pounds at $1.50 a pound, 3 pounds at $1.80 a pound, 5 pounds at $2 a pound. The weighted mean calculation is this formula here. You're going to sum up all of the data points multiplied by their weight, and then you're going to divide by the summation of all the weights. So WI is the weight quantity of each purchase, and XI is the price per unit per pound for each purchase. So purchase one here was 2 pounds at $1.50. 2 pounds at $1.50 is 3. So the weight here is $1.50, and then the quantity is the price per unit here is the 2. So XI is the price per unit, and the weight quantity of each purchase. So WI. That's interesting. It kind of got a little bit. So what I'm looking at here is ultimately I want to know the price. And so XI is the price. That's correct. XI is the price and WI is the weight. So here's my weight. Here's my weight. Here's my weight. Here's my price. Here's my price. Here's my price. And I want to know the average price per pound or the weighted mean that I purchased each of these beans for. Statistics can sometimes be, you just have to talk your way through it, navigate through it. And that's why sometimes I'm like finding my way with explaining this exactly the way it needs to be explained. So here the total cost would be $3, $5.40, and 10. It's $18.40 is the total cost. And then we sum up the total weight, it's 10 pounds. So if we paid $18.40 for 10 pounds, we paid $1.84 per pound, right? This time we paid $1.50 for 2 pounds. We paid $1.80 for 3 pounds. We paid $2 for 5 pounds. And when we add up all of the money that we paid $3, we paid this amount, we paid that amount, right? That's how much we paid. And the total number of pounds we bought, that's how many pounds we got. We get the weighted mean of $1.84 per pound. And so you do that with that formula there. That's what a weighted mean is, and that's how you calculate it. And then we also have the geometric mean. And the geometric mean is for data that compounds over time. And I can say, can you please also give me an example of using the geometric metric mean. And so we'll see this here in just a second. We'll let that come out. So it's used to calculate average rates of growth or returns over time, especially with dealing with percentages, ratios, or multiplicative processes. So year one, 10%, we have 1.10 as a multiplier. Year two, 5%, we have 1.05 as a multiplier. So let's say you're evaluating the average growth rate of an investment over 3 years with the following annual growth rates. In year three, we have 15% or 1.5 as a multiplier. And the geometric mean here is calculated with this formula right here. And the way that looks in action is 110, 105, 115 gives us this result right there. And then we take the nth root of that. So that amount divided to, the nth root of 3, 1 over 3, we get this amount every year. So the geometric mean growth rate is 9.75% per year. So here, right, if we were to calculate what's the average of this over time, we would say the average is 10%. Because 10 plus 5 plus 15 is 30, divided by 3 is 10%. But really, when you're compounding things each year, it's going to be 9.75% each year is, because year zero, we start with $1. And then at the end of year one, we have $1.0975. And then year two, we make another 9.75% on that amount. And we just compound that. And at the end of 3 years, we have this amount when we're compounding each year at that rate. So that's a little bit more involved, gets into the time value of money and compounding interest over time. So but that's what the geometric mean is used for. The main ones I want you to really kind of feel comfortable with are these right here: mean, median, mode, percentile, and quartiles. And then also we start talking about the interquartile range. So let's take a look at what is, continue to explore these. Perhaps the most important measure of location is the mean. The mean provides a measure of central location. The mean of a data set is the average of all the data values. The sample mean, x bar, is the point estimator of the population mean, which is mu. And so here's how you calculate the sample mean. And the sample mean x bar is equal to each of the individual data points, which is represented by xi, summing all of those up, which is represented by sigma, and then dividing by the number of data points or the number of observations in the sample. And then for the population, and here's actually an error, this should not be a lowercase n, it should be an uppercase n, but that's it. So here's mu, which represents the population mean, add up all the data points, divide by the total number of items in the population, and that's how you get the population mean. And so here's an example. So placement office wants to know the average starting salary of business graduates. Monthly starting salaries for a sample of 12 business school graduates is provided here. So here's 1 through 6 salaries, 7 through 12 starting salary. And to find the starting salary, we're going to add up all of these figures and divide by 12. And so here, when we add up all those figures, we get 71,280, and we divide by 12, we get 5,940. So on average, the average starting salary is $5,940. And then we could calculate the median. So the median of a data set is the value in the middle when the data items are arranged in ascending order. Whenever a data set has so median, the median of the road, the median of the data. Whenever a data set has extreme values, median is the preferred measure of central location. And the reason you want the median over the mean is because the mean can be swayed by outliers. And we saw that when I changed that one figure to 200, whereas the median is always going to be the same. It's the middle piece of data, right? Even if there's one data or two pieces of data way out there that's an outlier, the median shows us this is the middle piece of data. And the median is the measure of location most often reported for annual income and property value, which is kind of interesting. Maybe because we have some outliers with income and property value. And a few extremely large incomes or property values can inflate the mean. So there we have that. So for an odd number of observations, 7 observations, we put them into ascending order. The median is the middle value, which is 19. If you look at 19, you have 3 data points on the left and you have 3 data points on the right. So the middle, the median, the middle of the road, the middle of this data is 19. For an even number of observations, right, we put them into order. So we have 12, 14, 18, and then we have 27, 27, 30, and the middle ones are 19 and 26. We add those together, divide by 2, we get 22.5 is the median. And then our mode here would be 27, right, because that occurs twice. So the monthly starting salary averaging 6th and 7th data values, the median is going to be these two averaged, or 59.05, and just comparing that to the mean. So the mean is 59.40 and the median is 59.05. So again, this is just different ways we could start to talk about our data and describe our data, the mean, the median, and then we'll get to the mode in a second. Another measure sometimes used when extreme values are present is the trimmed mean. It is obtained by deleting a percentage of the smallest and largest values from a data set and then computing the mean of the remaining values. For example, the 5% trimmed mean is obtained by removing the smallest 5% and the largest 5% of the data values and then computing the mean of the remaining values. And the mode of a data set is the value that occurs with the greatest frequency. So the greatest frequency can occur at 2 or more different values. If the data have exactly 2 modes, the data are bimodal. And if the data have more than 2 modes, the data are multimodal. So we already saw examples of that with ChatGPT. And so here's an example of mode. And the mode here is 5880 because we have 5880 here and we also have 5880 here. And the data is in descending order. And so I'm just trying to 5710, 5755, 5850, 5880, 5880, 58. So it's going like that. But that kind of, oh, it's in ascending order. My eyes read that incorrectly. And then using Excel to compute the mean, median, and mode, you could pause the video here if you want to see how to do that. And there are your formulas for doing that. So that's how you do that in a spreadsheet. The weighted mean, we talked about this. In some instances, the mean is computed by giving each observation a weight that reflects its relative importance. The choice of weights depends upon the application. The weights might be the number of credit hours earned for each grade, as in GPA. In other weighted mean computations, quantities such as pounds, dollars, or volume are frequently used, depending upon what you're dealing with. Again, think of those black beans, price per pound. I like that example. And so here we have this formula where xi is the observation, wi is the weight of the observation for each data point I. You're going to sum those up when they're multiplied together and divide by the weights all summed up. Numerator is the sum of the weighted data values and denominator is sum of the weights. So up here we have price per pound and the amount of beans that we were doing. We want to know ultimately how much did we pay, what's the price. So the weight would be how much weight did we buy. We bought 2 pounds, 3 pounds, 5 pounds, and this would be the price we paid. And so we would have like a dollar, if this was 10 pounds up here, we would have $18.40 divided by 10, or $1.84 per pound that we paid, right? So 10 down here would be the number of pounds we bought, and this would be the total price we paid for all of those pounds. And then we'd find the weighted price, the weighted mean for what we paid, the average of what we paid. So here is an example. Cost per pound, number of pounds, and then here's how we calculate it. Cost per pound, number of pounds, and then here's our WXI. The cost is our X, the weight is actually the weight, and we calculate that right there. And then when we add all of those up, and this is just like, I have no idea why that's such a big number. So that should be 800, and 800 times 2.5, 2.5 would be, would that be right? 800 times 2.5 would be 1,600, and 400, that'd be 2,000. What times what times 800 equals 2,600? And do these add up? So we have to do a little math here. So 2,600, because there's an error in the presentation, 2,600 divided by 800, right, is going to be 3.25. So here we have 3.25 times 800, and we could check that. 3.25 times 800 is equal to 2,600. So we've got that, but now we need to check this here. So we could get all these data values here, copy those, and we come over here, and can you please add up these numbers for me? And we'll add those up. And just make sure that's correct in the presentation. And this is a 6250. And so 6250 is what we wanted down here. And so now when we add up all these numbers here, that should be 18,500, this should be 6250, and we get that, we get 296. So the weighted mean, the amount that we paid, is equally weighted simple mean is 307. So the amount that we paid on average, the weighted mean, is 296, and equally weighted, or just the simple mean, I'm going to do like the simple mean, and I'll do e.g. the equally weighted mean, because that kind of confused me when I read it, is $3.07. So if we didn't weight the mean, right, or everything was equally weighted, the average here is $3.07. So if we took this here, copied it, and we came over to ChatGPT, just check it. What is the average? What is the mean of these values? All right, we'll put that in, and that should give us $3.07. Yeah, perfect. All right, and then the weighted mean is 296. So that's the weighted mean. And then here we have the geometric mean. And we've talked about that as much as I feel you need to know about it. So you can pause the video and just read about this here. And you could pause the video and you could take a look at that here. And you could pause the video and you could take a look at the data here. And then you could pause the video and you could take a look at the data here. And there's the average compound rate. But something to know when you go to make investments is you just want to like take a finance course, personal finance course, and really make sure you understand compounding rates. And then using Excel to compute the geometric mean, we're just going to skip that here. And now we're going to talk about percentiles. So a percentile provides information about how the data are spread over the interval from the smallest value to the largest value. Admission test scores for colleges and universities are frequently reported in terms of percentiles. The pth percentile of a data set is a value such that at least p% of the items take on this value or less, and at least 100 minus p% of the items take on this value or more. So if we are at the 80th percentile, p percentile, 80th percentile, right, 80% of the items take on this value or less, and 100 minus 80, which is 20%, 20% of the items take on this value or more. So again, statistics can have a way of making things overly complicated. I feel like the way that's described is a little bit overly complicated, but when you say, hey, 80% this value or less, 100 minus 80, which is 20% this value or more, that totally makes sense. And so here's that formula for calculating that. I also have that formula on this sheet here. You should maybe pause the video and take a picture of it with your cell phone so you have this to reference. But there it is right there. But that's how we do it. And then the 80th percentile, right? So we would add 80 over 100 for like these 12 items. It'd be 12 plus 1. It'd be 10.4. And so 10.4, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 40% of the way between 60/50 and 61/30 is going to be 61/30 minus 60/50 times 0.4. So 60/50 plus that amount brings us to 60/82. So 80% of the data is at 60/82, 6,082 or less. 20% of the data is above that. So that's the 80th percentile. And so here's a description of that. And it says, at least 80% of the value of the items take on a value of this or less, right? So that's 10 over 12 is 83%. 10 over 12, I'm not sure what the 10 over 12 is doing there. And 2 over 12 is 16.7%. And then 20% of the values, so here's 10 over 12. So we're a little bit we're a little bit past that. At least 80% of the values take on 60, 82 or less. And 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I'm not sure what that is doing there and what they're trying to convey with that. But 20% of the values take on that or more. So we'll just ignore this part. I wonder if I could take that out. It's a picture. I can. Quartiles are specific percentiles. So first, second, and third quartiles, 25th, 50th, and 75th percentile. This is also known as the median. And the third quartile, right, 75th percentile, if we calculate that, we get 9.75. So 75% of the way between these two figures is 0.75 times the difference between 6050 and 5950, so whatever that distance is. And then we add that to the bottom figure, 5950, and we get 6025. So 75% of the data is at 6025 or less, and 25% of the data is more than that. And then using Excel to compute percentiles and quartiles, we're not going to worry about that right here. And then we have measures of variability. So measures of variability brings us into moving into this next part here. I kind of want to save this for the next video, but I think we'll just power through because it's getting late and I want to get this done. So measures of variability, it's often desirable to consider measures of variability or dispersion as well as measures of location. Remember, not only like what is the measure of the location, what is the mean, what is the median, what is the mode, what's the percentile, what are the quartiles, but also how dispersed or how much does this data vary, right? And so we want to not only consider measures of like where's the data located, right? It's often desirable to also consider measures of variability or dispersion as well as measures of location. For example, in choosing supplier A or supplier B, we might consider not only the average delivery time for each, but also the variability in delivery time for each. So we were talking about that. And so measures of variability include these: range, interquartile range, variance, standard deviation, coefficient of variation. And the range of a data set is the difference between the largest and smallest data values. So here the range is one way we could think about variability. And so if we came over here and we looked at the range of this one, right, we could say, hey, what is the range? And the range is the difference between the biggest and the smallest values. The range here is going to be 12 minus 8, which will be 4, right? So that gives us a sense of variability. It only varies by 4 days, whereas the range here is 28, right? Like way more variability, you know? So range is a way that we think about variability. The largest value minus the smallest value. It's the simplest measure of variability. It is very sensitive to the smallest and largest data values. And so here is calculating the range, and the range here is 615, right? I really think that range is better illustrated by comparing that example there. And then we have the interquartile range. We already talked about this, but we're going to go through it because repetition is the mother of mastery and practice makes progress. And the more you're exposed to something, the more it seeps into your brain. The interquartile range of a data set is difference between the third and first quartile. It is the range for the middle 50% of the data. It overcomes the sensitivity to extreme data values because you're basically throwing out the data in the first quartile and in the top quartile, right? Everything above 75 and everything below 25. And you're keeping everything between 25 and 75, which is the middle 50% of the data. So you're throwing away those outliers on both sides. And so the interquartile range, if the third quartile is this and the first quartile is that, we subtract the third from the first and we get, this is the interquartile range. And the variance, and then we get to variance, right? So that's interquartile range. And interquartile range will be used when we multiply this figure here, 167.5, the IQR, by 1.5. We could use that as a way to sort of benchmark or test whether or not data is lying outside, is an outlier, right? If it's too far away from the, you know, the more central data. So next thing we're going to talk about is variance. And so variance, so if we have this data here, right? One of the things we could do, and this is the mean right here, so I'm just going to copy the spreadsheet. So I'm going to copy it, and I'm going to choose duplicate right there. And so I'm going to just click down here and call this variance. And then I'm going to right click up here, and I'm going to choose insert a column left. And then I'm just going to put variance right here, and I'm going to do variance right here. And I'm going to and I'll make this one yellow. Boop, 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 boop. And I want that to be yellow. And then we'll make this one blue. Boop, 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 boop. And I guess that's close enough blue. That might be the exact same blue. And here for the variance, I'm going to take this data point and I'm going to subtract it from the mean, and I'm going to hold that constant as I move it down. Okay? And no, I'm not going to fill that in right here. And so the variance is going to be your data point minus the mean. That's the first part of the variance. So I'm going to copy this and paste it down. And so you're looking to see how much does each data point vary from the mean right here. So we'll just also highlight this one here, the mean. That's important. And notice what's interesting is that it varies -2 on, this is a little bit to the left of 10, which is the mean. It's -2 from the mean, so 2 less than the mean. This one varies 2 less than the mean, which you see right here. This one varies 2 more than the mean. This one varies 2 less than the mean. This one varies 2 more than the mean. This one varies 0 from the mean. And so variance, how much does each data point vary from the mean? And then all this, because like if you have the mean is like the measure of central tendency or central location, which means it's in the mean is like, it's got the stuff varying the same on one side versus the other. And so these add up to 0, which is kind of interesting. If you add all those up, they add up to 0. And if we do that here again, we say how much does this data point here vary from the mean, like right there. And I'm going to make that absolute reference, make it a D8, put the $signs in front of it by pressing F4. And I'm not going to fill that down, but I will copy it, and then I will paste it down. So this data point here varies this much from the mean. So 30 is 20 more than 10, right? This 30 varies 20 from the mean. This 5 varies -5 from the mean. This 10 varies 0 from the mean. This 2 varies -8 from the mean. This 3 varies -7 from the mean. And if we add all these up, 7, 8, 15, 7 and 8 is 15, and 5 is 20, all negative, and 20 there, those add up to 0. So that's kind of an interesting deal. And I'm going to insert a column to the right of this, insert column to the right. And now I'm just going to multiply this by itself, okay? And that is, in effect, squaring it. And so I'm going to now copy this and bring this down, paste that down. And so -2 times -2 is 4, 2 times 2 is 4, -2 times -2 is 4, 2 times 2 is 4. And so now I've multiplied it. Because when we calculate the variance, we find the difference between the data point and the mean, and then we square it. We square it to get rid of the negatives, okay? We square it to get rid of the negatives. And then we're going to add all that up. So if I add all that up, I'm going to look, there's the sigma. I'm going to sum all that up. I'm going to sum all that up. I get this. And then if I take that right there, and I guess I'll put, variance here. And if I take that, and then that's 16, and it's going to be equal to 16 divided by, and I come back over here, and I see it's n plus 1. I have 1, 2, 3, 4, 5. So 5 plus 1, which is 6, right? If I divide this summation of the difference between the data point and the mean squared, which gives me these numbers, add all those up, and then divide that by n plus 1, that's how you calculate the variance. 2.67. And so I could do the same thing over here for this one. And to do that, I'm going to insert one column to the right just to get the color. And then I'm going to do equals to this times this. And I'm going to, oh, yeah, that's right. Now I'm going to copy these down. And so now I'm going to sum those up. And sum all those up. And then I'm going to come down here and I'm going to say it's this amount divided by 6, which is n plus 1, or 5 plus 1 is 6. And I get that. And so you can see that this has a much lower variance, just like as a number to sort of measure like how much did things vary. This has a much lower variance than this one. That one has a much higher variance. So that's how you calculate the variance. And then the way you calculate, and for a sample population, use S squared. For a sample variance, use S squared. For a population variance, use sigma squared. For a sample variance, use n plus 1. For a population variance, use capital N. And then we have the standard deviation. And so to calculate the standard deviations, we just take the square root of each of those. And so the square root of each of these is, I don't know, I think there's a square root formula. There it is. And the square root of this, right, is that. And this is going to be our standard deviation. So our standard deviation. And these are just measures of like how much is the data varying, how much is the data dispersed. And if we do the same thing here, I could just copy this formula here and, oops, copy it there and then put it here. And let me just check that. That's the square root of that one. So that one's working right. And so you can see the standard deviation is 1.63 and here the standard deviation is 9.46. Like what is the standard amount that the data deviates or from the mean, right? From the mean. How much does the data deviate? What's the standard deviation from the mean? This is a measure of it. It's 1.6. And then finally we have the coefficient of variation, where we take the standard deviation, we divide it by the mean, and we multiply it by 100. So the coefficient of variation here is we take the standard deviation, we divide it by the mean, and then we multiply it by 100. Okay? And so the coefficient of variation is that. And then if we do the same thing here, we take the standard deviation, we divide it by the mean, and we multiply it by 100. That's pretty cool how the computer was already prompting me with that. And then we get that right there. So let me just check to make sure that's right. We have G12, E8, 100, and we have D12, B8, and 100. So pretty interesting. So that's the coefficient of variation. So if we come back here and look at these slides now, we'll go through and see how they're explained. And I'm just going to check to make sure my video is still recording, and we're looking good there. So the variance is a measure of variability that utilizes all the data. It is based on the difference between the value of each observation and the mean. So the difference between the value of each observation, so observation and the mean. So, you know, this minus that, or the mean minus this. So the variance is calculated by your data point minus the mean. Your data point minus the mean is that. And so that's, you know, the difference between the value of each observation and the mean. And so here's the formula, each observation and the mean. And I just think that's worded a little weird. The variance is useful in comparing the variability of two or more variables. And so for a sample, for a population, those are the formulas. And the variance is the average of the squared differences between each data value and the mean, right? So that's kind of interesting, the average of the squared differences between each data value and the mean. So how much does each data value? It's like if that's how much each data value varies from the mean, the variance shows us the average of how much each data value varies from the mean. So the average of how much each data value varies from the mean here is 2.67. Here it's 89, right? G7, 538 divided by 6. And here it's D7, 16 divided by 6, which is a pretty big difference, but it's the average of how much each data point varies from the mean. And then, you know, the standard deviation of a data set is the positive square root of the variance. It's measured in the same units as the data, making it more easily interpreted than the variance. And so we just take the square root of each of those to get the standard deviation. And so we're not going to worry about how to do that in Excel, so let's get rid of that. And then the coefficient, I'm just making sure, Excel's variance, yeah, we don't need that. And then the coefficient of variation indicates how large the standard deviation is in relation to the mean. So the coefficient of variation is computed as follows. So standard deviation over the mean. So, you know, it's the coefficient of variation indicates how large the standard deviation is in relation to the mean. So here we have the standard deviation, right? And here we have the mean. And when we take the standard deviation and we divide it by the mean, so D12 divided by B8, we get, you know, a number, and then we multiply that by 100, we get 16.32, right? And so the coefficient of variation indicates how large the standard deviation is in relation to the mean. How large the standard deviation is in relation to the mean. How large the standard deviation is. How large the standard deviation is in relation to the mean. So it's kind of interesting with a mean of 10, we're getting just basically a movement of the decimal point, but that's what the coefficient of variation is. And sample variance, standard deviation, and coefficient of variation. Monthly starting salary, and we'll do an example here in ChatGPT to also cement this. So here's monthly starting salary, variance, standard deviation, and then coefficient of variation. And then we're going to pass on using Excel, and that's the end of this part. So I'm going to copy these here, and I'm going to go over to ChatGPT, and I'm going to say, can you please explain the following to me, and also provide me with a simple example to help me understand. Boom. Let's break down each of these concepts: sample variance, standard deviation, and coefficient of variation. I'll provide simple examples to illustrate each one. Sample variance. Sample variance is a measure of how much the values in a sample differ from the sample mean, right? So how much the values in a sample, each value is xi, differs from the sample mean, which is x bar. It quantifies the dispersion or spread of the data points around the mean. And so this is like the average, so we do n minus 1 here, and n minus 1, and I have n plus 1 here for variance. So that's kind of an interesting thing. It gave us n minus 1, and I have n plus 1. And so I'm going to go to Google and say variance formula. And at Google, we get n minus 1. So I made a little bit of an error in my notes here. Just checking that. And so again, here it is in our presentation as n minus 1 from the textbook. So if we fix these here, my n minus 1 here would be 4, right? Instead of 5 plus 1, it's 5 minus 1, so that's 4. And then this one here is going to be, instead of 6, it's going to be 4 n minus 1. And so that makes these numbers a little bit smaller and more reasonable. So that actually looks somehow more reasonable. So that's good that we caught that. So n minus 1. And so here's an example. Calculate the mean. So our mean is 4.8 with these test scores. And subtract the mean from each value and square the results. So 2 minus 4.8. 4 minus 4.8, and we square each of these and we get these numbers. And then we're going to sum the square differences. We're going to add those up, 20.8, and then divide by, and this is known as degrees of freedom, n minus 1. Divide by 4, we get 5.2. And so that's our variance. So the sample variance is 5.2, right? Which is the average of how much data point varies from the mean is 5.2. It's 5.2. Is that how much it varies from the mean? And then we have a standard deviation. So we take the square root of that. Square root of 5.2 is 2.8. And the standard deviation is the square root of the variance, provides a measure of the average distance of each data point from the mean, is in the same units as the data, making it easier to interpret, right? We squared everything up here to make it positive, but that also made the numbers bigger. So if we take the square root, that brings it back down to the size of the numbers we worked with and makes it easier to interpret in relation to the units of the data. And so if we look at that here, This is larger. We take the square root, it's smaller. This is in the units of the data. So the amount that each data point, the standard deviation of a data point around the mean is 2. The mean is 10, and the standard deviation is 2, right? This is 2 less than 10, 2 more than 10, 2 more than 10, 2 less than 10. So the standard deviation is 2. That kind of makes sense. Here, where we have less even distribution and variance, dispersion, right? If the mean is 10, we have some stuff that's like 20 away from 10 and some stuff that's 8 away from 10, but the average deviation of each data point is 11.59. So that actually just became a little bit more clear to me. And statistics is that way. You just kind of have to keep working it until you kind of go, oh yeah, that just made a little bit of sense. And so, this data point here is like squared, so it's at a different scale than the data we were working with. So it's hard to kind of relate it back to this squared value. But when we take the square root of that value and get this value, that's easier to relate it to this. And so on average, the amount that a data point varies from the mean is 11.59. Here, the amount that a data point varies from the mean is 2, right? And you can see that pretty clearly here, which is kind of cool. And then we have coefficient of variation is the ratio of the standard deviation to the mean. And it's expressed as a percentage. It measures the relative variability of the data, providing a way to compare the degree of variation from one data set to another, right? And so here, if we have different means, so here's 10 and 10, it really doesn't make a difference. But if we had different means, we'd be able to compare those different means by getting the coefficient of variation, because it would show us how many of the, so coefficient of variation is the standard deviation divided by the mean. So if the standard deviation was like 10 and the mean was 5, it would be like 2, right, is the amount. And so it gives us like a scale which can be compared between different data sets of different values. So that's what the coefficient of variation does, is the ratio of the standard deviation to the mean expressed as a percentage. It measures the relative variability of the data, providing a way to compare the degree of variation from one data set to another, regardless of the units of measurement. So here's an example. Using the mean and standard deviation calculated above, we get a coefficient of variation of 47.5%. So the coefficient of variation is that. Sample variance measures the average of the squared differences from the mean. Standard deviation is the square root of the variance, giving a measure of dispersion in the same units as the data. And coefficient of variation expresses standard deviation as a percentage of the mean, useful for comparing variability between different data sets. Why these measures matter? Sample variance and standard deviation help in understanding the spread of data, which is critical in fields like finance, engineering, and social sciences. And coefficient of variation allows for comparison of variability across different data sets, even if they have different units or scales. All right, so that's, a little bit to wrap your head around. And we kind of came at it from a couple of different angles and had repetition to hopefully drive that information home and to create clarity. But it is, this chapter takes a little bit of time to understand. So do the homework, work the assignments, come back and watch this video. You could, read through the textbook, and all that's going to help you get it. And you can look at this here. But that's the first part of this module number 3 and chapter number 3 in the textbook.